Okay, back by popular demand, we have a little bit of work on impulse and momentum. Now, this is a topic that I know there's a lot of words in this, and I think it's important that you learn the definition of the word. So, impulse and momentum. First of all, momentum. Momentum is given the symbol lowercase p in physics. Okay? Uppercase P is for pressure. So, lowercase p, and it's the product, i.e. what you get by multiplying mass and velocity. And that is all in lowercase. Now, I have lost my felt tip pen, or rather it's run out and I haven't managed to chase it. In terms of units, because the mass is in kilograms and the velocity is in meters per second, the unit of momentum is kilogram meters per second because you're multiplying along the line. So those kilogram meters per second, which of course, if you do meters per second the other way, it could be kilogram meters per second like that. Now, you do know about momentum. Objects with a lot of momentum command respect. You're not going to argue with 1,000,000 kilogram meters per second of momentum because you know it's a lot of mass and a lot of speed, or it's something with a small mass moving at an enormous speed. So something with a lot of momentum swings to mind is a lorry. In the UK, you can make lorries that are 40 metric tons, or 40,000 kilograms, and they're allowed to go at 60 miles an hour, which is approximately. So you can see, if you substitute into the equation, 60 miles per hour is about 20 meters per second. If you substitute in the equation, you get that's nearly 1,000,000 kilogram meters per second. That's a lot of momentum. You know you don't want to mess with that. That's going to carry on doing whatever it's doing. It's got a lot of inertia and it's got a lot of speed. So it's going to cause problems. So, whereas, if something a lot less consequential, not mentioning any names, like Babyface ran into you, you'd barely notice. Okay? Now, so, in a collision, momentum is conserved if no external forces act. And the most obvious external force is gravity. So, whenever we do, this is called the principle of conservation of linear momentum. So that was the PCLM when I was at school, the principle of conservation of linear momentum. And we do these things where you have momentum before equals momentum after. I've got my two cars, and these are math routines that you're generally quite good at. Sometimes you forget that this velocity might have a minus sign. You'll have to put that in when you substitute in the value before you multiply. But generally, you're quite good at this. And I'm happy to go through those examples if you want to. That's not really the issue of what impulse is. So I thought I would move on. Impulse is the product of force and time. And that equals the change in momentum. So here I've got the mass times the final velocity. If you subtract from that the mass times the initial velocity, we get the change in momentum. So impulse equals final momentum minus initial momentum. So I thought it'd be better to do an example rather than sort of flounce around saying what it is. So now, collision with a floor. The floor provides a force. So you get a change in momentum. Now, and it often confuses people, this. So let's look at this. Imagine you've got a basketball about 0.5 kilo in mass, and it's falling to the floor. And just before it hits the floor, it's got a velocity of 4 meters per second. Maybe this is not perfect. Maybe I should have drawn the basketball sort of just like tiny, almost about to hit the floor, sort of like this. But I thought if I do that, I won't have enough room to get the arrow in. So that's why I've done it like this. Anyway, here's my basketball. So let's work out the change in momentum. It's momentum before it's going at 4 meters per second into the floor, and it bounces off, and it's going slightly slower as it bounces back up. So this is the final state. So I've got that. This is final, and this is initial. And because this is all about the bounce, which is the collision with the floor. So my final is going to be the mass, 0.5, times by 3. Now, I've got to decide which way is positive and negative in my diagram. So it isn't a problem as long as I'm consistent. So let me say that up is positive. So I'm going to label that, and that is to tell anyone that's marking this that I know that up is positive. So the final momentum is up 3 times by 0.5. So that's okay. Now the initial momentum has to be negative because it's in the opposite direction, and I decided that up is positive. So when I'm going to do this subtraction here, I'm going to put these in brackets to keep these multiplications separate from the subtractions. I've now got, my velocity is now minus 4 multiplied. So I've got 0.5 multiplied by minus 4. So when I do that, obviously these are half times 3 is 1.5 minus, and the product of 4 minus 4 and 0.5 is minus 2. So when I do 1.5 minus minus 2, I get a change in momentum of 3.5 kilogram meters per second. Okay? So that is something you're going to have to work through very carefully, that you've got to pick a direction for positive, and then you've got to sort out your velocities and then substitute into what is after the collision with the floor in this case, what's before the collision, and work out your change in momentum. Okay. And then naturally, that would lead on to being the force that the floor acts multiplied by the time equals this change in momentum. So the impulse equals the change in momentum. And that would be what this went on to give us. Okay, impulse equals change in momentum. Okay, let's work through another example. So here I've worked through an example with a golf ball and said a golf ball of mass 50 grams is hit by a club and it leaves the club head at 60 meters per second. Okay, now have I drawn a picture? I've drawn a picture on my introductory page. Let's consider a golf ball being hit by a club. The club gives a force which acts on the ball. Or to be in more sort of physics speak, the club exerts a force on the ball. Okay, and this will be for a small time interval that we'll call t. So we're going to have an F from this and a t from that, and already you should be thinking impulse equals force times time, and we know that that will give us a change in momentum. So that is where we are going. We're going golf ball, club exerts a force, it happens for a small time, of course. So back to the maths. How does the maths work? Well, the first question is, the mass is 60 grams and the ball leaves the club head and at 60 meters per second, which is obviously pretty fast. So 60 meters per second is about 10 meters per second is like a sprinter runs, which is about 30 miles an hour. So 60 meters per second is about 120 miles per hour. So that's pretty fast. So find the final momentum of the ball. So when you hit the ball, initially the ball is at rest. So it's sat on the little T thing, just like being a golf ball. Whack. So then it moves off at speed. And at this point, it's got velocity. So we're saying at this point, it's got velocity. Now, how much momentum does it have when it has that velocity? Answer, take the mass, multiply by the velocity, and you get the momentum. Now, take great care with your gram conversions. So 50 grams is 0.05 kilograms, and that gives me 3 kilogram meters per second of momentum in the ball. Now, if the ball was in contact with the club for 4 milliseconds, watch out for that. So that 0.04, so divide by 1,000. Find the average force of the club. Now, if you've got a change of momentum you already know and you're being asked for a force, the only equation that we're going to link these two together is our impulse equation, which says that force times time equals change in momentum. So we substitute in. Now, this is an easy one because at the start, the golf ball had no momentum because it had no velocity. So way back up there at the start here, when it was just sat on the tee thing in the grass, the golf ball had no velocity and therefore has no momentum. So this makes this question particularly easy compared to the bouncing on the floor. mu is 0, my final velocity is 3, so my final momentum is 3, that units of momentum, kilogram meters per second, that I've got from up there. My time is 4 milliseconds, and my force I want to know. And when I do that, I get 750 newtons, which seems fine. It's a big whack, and the ball goes. Okay, now, okay, so what have I got to finish up with? Graphs. Now, for the golf ball question, you could have been given the information in a graph, and you wouldn't necessarily, and you could have been asked to plot a graph, or you could have been asked to do something with a graph. Now, in my survey of recent experiments, recent exam questions, there were not graphs on recent exam questions, but there were in historic exam questions. So for that force, you might find that we had 750 newtons that acted for 4 milliseconds. Now, if you do get a graph, watch out for people putting the crafty milli in there. And many people end up using that would end up using time equals 4 seconds, not saying, oh no, it's in milliseconds. So time is actually 0.004 seconds. Okay, so that's a common mistake to make. And of course, in a real world, golf ball, you wouldn't get something like this. You get some kind of strange force function where in the real world you get some sort of, initially the ball bends a bit, which reduces the force on the ball. So you get some kind of sort of like, so you get something strange like that. And so, but in exam land, obviously things are somewhat simplified. The only other thing I would say about in exam land is I have seen exams where you get a triangle, and if you do get a question in exam land, it's important that you realize that the area under any one of these graphs, the area would be calculated, so any area in here would be calculated by multiplying some force by some time. Now, what does force times time equals? It equals impulse. So the area under a force time graph can be used to calculate impulse. And then a question might lead you on into finding a change in momentum. So I think you've got to watch out for, if you do get a question, you might well get a question that has got a triangle, and you have to find the area of the triangle using the half the base times the height, and that will equal your impulse. And watch out for this being in milliseconds, which is quite popular. However, so area is the key point there, and watch out for those force multipliers. The most recent questions simply want you to work out impulse equals change in momentum by doing impulse equals mv minus mu. So if you want to have a little practice at this, you could have a go at section B questions from 2017, question 2B, and 2019, question 1B. So those are things that you can do on impulse and momentum as a bit of a challenge and see how you get on. Alternatively, you could actually work through your textbook questions, and if I can just move this across, the textbook questions here might be a better place to start. So you could do these questions that are from page 50 of the textbook. Might be a more gentle place to start. Do the page 50 questions, and then when you're happy with those, then do the exam questions from 2017, question 2B, 2019, question 1B. Okay.